multi-system performance, then why we should go for phone recognition system? This is one question. Because speech recognition system gives better performance which language models, because we know that there is a certain grammar in any language. So that can be used effectively to give a good performance. In the phone recognition system, there is no such knowledge. Any phone can follow any other phone. Why is this required? There are different applications. Speech recognition system has got a different application. You talk to a computer or you talk to a remote information retrieval system to get some information like train information or something like that, or air travel information, and through the telephone. That is the application of a speech recognition system. But the phone recognition system has got a different application. One application is keyword spotting. There are huge amounts of spoken documents, maybe lectures, video lectures, audio lectures, and many such documents. You want to query the document without actually going through the document and pick up those documents and segments of those documents which has got that particular keyword which you are interested in. This query can be just at a word level or even at a semantic level, at the phrase level, or different kinds of querying can be posted. That is one important application of, and that too, this is also useful in multilingual environments. There may be documents spoken in many languages, so you want to retrieve those documents which has got certain keywords. Another application is language identification. We know that we don't know most of the Indian languages. Probably many of us know maybe one or two, maybe Tamil, Malayalam. But hearing some other German or Latin with some training, we can identify, not actually understand, that is German, this is French. This is possible at many levels. Many levels means we apply the morphological knowledge and also the prosody. That is the variation, some variational pattern we capture in each of the languages, and then that we use. More than that, we try to decode the sentence in terms of the sounds we know, and then express how frequently a particular sound follows that. Some statistical analysis we do ourselves without our knowledge. That means, I will come to the details later. So what it means is that a phone recognition system, that means if I know Tamil, and it is not necessary for me to know French, Latin or German to be able to just say that is that language. That is achieved with the help of a phone recognizer. Then it is also possible to identify speakers just using phone recognizers. So speech, we know most of the telephone quality speech contains a signal up to 8 kilohertz. And our CD, it has got 16 kilohertz quality. That means the signal is sampled 16,000 times per second. That is what it means. So there are many features which we try: filter bank output energy, MEL frequency capsule coefficients, linear predictive coding, perceptual linear predictive coding, MEL frequency capsule coefficients. All these things we have tried, and popular feature in this is MEL frequency capsule coefficients. Why is this popular? This is popular because all the frequencies are not equally important for human beings. The one example is, we know the telephone, when we speak, sometimes we may not be able to identify the person on the other side. It's because the telephone quality speech, the bandwidth, the signal frequency is only up to 3 kilohertz, whereas the CD quality which we hear is up to 8 kilohertz. Which means that the high frequencies are not so important. This particular aspect is used in MEL frequency capsule coefficient. That's because of that, it has got better performance for speech recognition systems and phone recognition systems. This is our baseline system, and my effort was to see how to improve the performance of the system by using some other features, some other architecture. Here, most of the time, we use hidden Markov models. I will not go into the details of the hidden Markov models. It's a bit theoretical. But it's a statistical framework where we model each of the sound using some states, and each state has got a probability distribution. That means if the feature, this is a two-dimensional feature space. So if the feature is in this part, it corresponds to some sound, because this produces higher probability. If the feature is in this red space, this has got a higher probability, and that means that sound, that segment of the speech corresponds to that particular sound. That is the basic idea behind using statistical models for speech recognition and phone recognition. Then there are several segments of speech. It is not just one small segment of speech. Then how do we finally make a decision? We make decisions at every level and see which sound it corresponds to. And finally we come here and see what is the sequence of sounds that is the most probabilistic sequence. That is called Viterbi decoding. So this is what we use for phoneme decoding. And this we have seen, it is reasonably good performance. For example, Tamil, we get about 93% word recognition accuracy for about 1,300 words, and about 52% accuracy for phone recognition without using any other knowledge from the language, which is fairly a good number. So, but we wanted to improve the phone recognition accuracy. So what we did is, here we have used a Gaussian mixture model for modeling the probability of every sound features. In this case, we use a neural network to derive the probabilistic features. So what we do is, not only that we assume that the speech spoken at any particular time is important, we also take care that the variation in the properties of the speech over the time is also equally important. So we process the signal in the temporal domain, in the time domain, and we use some processing on top of this in addition to the frequency band parameters to enhance the performance of this phone recognition system using Hidar-Markov model neural network approach. So this is the architecture of the system. We have one left contact system to derive the probability and a right contact system, and finally we merge those probabilities to get the probability for different sounds. So that is the basic implementation scheme. The system is more sophisticated, and it's just, this is the basic principle of the system. And when we record speech, we label them as words, because it's very hard to label as phones. Because sometimes the phones themselves, it's not clear. It may be merged in the normal conversations due to co-articulation effect. So what we did is, we developed the grapheme to phone conversion software using rules. So these are the typical examples of the output of the G2P, grapheme to phoneme conversion software, which converts the speech text to phoneme labels, which we use to train the phone recognizer. So we need labels. Okay, every frame, what is the phone corresponding to that? That is the labels. So we use that to train the models, and finally we run without the labels to identify the phoneme sequence for the unknown test speech. That is the basic way of working the system. And there is one problem with the doubling of the sound. Like what we did is doubling of the sound. We inserted a short pause in between with the same phone on the left side and the right side. But experiments show that it is not necessary to do that. It's just necessary to have one phone with a short pause to reproduce the doubling effect. Which means that though this is theoretically correct, practically this has been found to be more correct. The systems recognition accuracy, so the Tamil is here. We have about 52.21% for